Some molecules have more than one valid Lewis structure. So let's look at ozone. Ozone is O3. So we've got 3 oxygen atoms. There's really only one way to do this, to put them in a line. We have 3 oxygens times 6, so 18 valence electrons. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18. Not quite enough. But we can give all these oxygens an octet if this guy in the middle that has an octet is willing to share a lone pair with the guy on the end that does not. I kind of feel like this might make a good, preschool story or something. Just sharing and making people happy. So let's just spread that out a little bit. Okay? So I'm going to draw that a little neater over here. So these are 3 oxygen atoms, and they are the same as each other, but they are not the same atom, right? So imagine a set of triplets, identical triplets. They have the same DNA. They may look exactly the same. Are they the same person?
No.
Absolutely not, and they'll be very unhappy if you think that they are, because they are individuals, right? So these oxygens are individual oxygen atoms, and this guy's saying, why does the guy on the other side get the double bond and I've only got a single bond? Why don't I get the double bond and he has a single bond? There's no reason. It's just because of how I happen to put the dots around. So let's draw it the other way as well, with the double bond at the other end. Those are equivalent, right? They are valid Lewis structures for this molecule. Well, how can it have 2? It can't. It turns out that the actual molecule exists as an average of these 2. If we look at the ozone molecule, we find out that the bonds between these two oxygens, that bond and this bond, they are identical. There's not a double and a single. There's 2 identical bonds. So what's really existing is sort of an average of the 2 of those. Well, Lewis structure can't handle this very well, and so what we do is we draw both structures, and I drew these too close together, and we put a double-headed arrow in between to indicate that these are resonance structures. The word resonance always suggested to me that we were resonating back and forth, right? That they were trading off who got the double bond. That's not how it is. The actual structure is a resonance hybrid. It's not this or that. It's the combination. The best we can do here is really to draw like a 1.5 bond for each. A single bond and then a dashed line to represent part of a single bond. Lewis theory just can't handle this. But this is like if you had a German Shepherd and a white lab and they had a puppy, and maybe the puppy looks like this. The puppy looks like that every day of the week. The puppy doesn't look like a German Shepherd one day and a white lab the next day. It doesn't vibrate back and forth between looking like 2 different dogs, right? It's always this combination of the 2 parents. So this is the resonance hybrid. The problem with the Lewis model is that we can't draw the actual structure of the resonance hybrid. Okay? In the Lewis model, electrons are always localized. the electrons are between these two atoms, or the lone pair is on this atom. But in real life, the electrons can be delocalized. They can be shared across the whole molecule. And so that second bond here doesn't go between either pair. It's actually shared by all three of them at the same time. Lewis model just can't account for that. It makes the molecule more stable, and so by lowering the potential energy, and it's called a resonance stabilization, and that shows up a lot in OCHEM too. Any questions? Mm-hmm.
What have to do with quantum mechanics? They just all three.
No, it's not really a superposition sort of situation. But that's a good question. It's a good question. Write a Lewis structure for the nitrite ion NO2 minus. Include resonance structures. So we've got a nitrogen and two oxygens. Like, well, do we put the nitrogen in the middle and the oxygens on the sides, or we put an oxygen in the middle and a nitrogen on one side and oxygen on the other side? Usually the more symmetrical is correct. And also if we look at who's more electronegative, oxygen's more electronegative. So we should probably put oxygen on the outside and nitrogen on the inside. So we've got nitrogen with 5 valence electrons. We have 2 oxygens. They each have 6. And the negative charge means we add an electron. So that gives us, 18. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. It's 3 atoms and the same number of electrons, just like ozone. We're going to end up with the same issue, right? So we can move those electrons over to share them so that this oxygen has an octet, 2, 4, 6, 8. The nitrogen, 2, 4, 6, 8. Oxygen over here, 2, 4, 6, 8. But, oxygen over here is going to be a whiny little baby. Why do they get the double bond and I can't have the double bond? Well, there's no reason. Let's draw it that way too. And then the other thing we need here, because these are ions, is we need brackets in the charge. That got kind of close. So those are the 2 resonance structures of NO2 minus. Most of the resonance structures we're going to see, they're always going to involve a double or a triple bond, and it's just a matter of where are we putting it. Here, between nitrogen and oxygen, or this is just another oxygen, these are equivalent, right? So this one or that one, we can draw both. Yeah?
Can we also draw like the dots over the single bond to represent that?
You could. The problem is if you try to represent this as a 1.5 bond, right? Where do you put all the lone pairs? Right? Because if the double bond's here, we've got 2 lone pairs. The other one has 3 lone pairs. And so I can't put the lone pairs around. And that's really where the problem comes. Any other questions? Which structure is not a resonance structure of this ion? Resonance structures differ only in electron placement. So, are all of these exactly the same except for where the electrons are? They all have the same number of electrons. This one, we've got a triple bond and a single bond, and so here we split it up more equally, 2 double bonds. But how is B different than that? But it's got nitrogen in the middle. The skeleton is different. That's not a resonance structure. Resonance structures, it's only electrons that are moving around. And since this is a different skeleton structure, the bonds are between different elements. This cannot be a resonance structure of that one. Sometimes we have to choose between a couple of different Lewis structures, and formal charge is a way that we can see which one's better. So formal charge is another one of those made-up things, a little bit like oxidation states. So it's a fictitious charge assigned to each atom. We don't need to consider electronegativity. And the way the book explains it, I think, makes it sound more complicated than it is. A formal charge is the number of valence electrons that atom has minus the number of bonding electrons and number of non-bonding electrons and half the bonding electrons. I can't even say it. I'm going to show you an easier way to do it. But these are the general rules, which are going to sound a little bit like those oxidation state rules. The sum of the formal charges in a neutral molecule has to be 0. The sum of the formal charges on an ion has to equal the charge. And this is the way ionic charges work as well. Small or 0 formal charges are better. Sometimes you have to have formal charges, and so we should put negative formal charges on more electronegative atoms because they're more attractive to the electrons, and so that's where that extra electron is going to want to go. So here we have 2 different structures. These are not resonance structures, but they are 2 valid Lewis structures for HCN. We're going to look at the formal charges. So this is how I think of formal charges, because I have to make everything act like people, right? So the way I think of this is hydrogen and carbon and nitrogen decided to form a business together, right? And they all brought some resources to the business, right? Hydrogen brought 1 valence electron, carbon brought 4 valence electrons, and nitrogen brought 5 valence electrons. So they've been in business for a while, and now something went wrong, and they're going to split up the business. So we're going to do that by just cutting the bonds in half. And so each of these atoms gets half the bond. There's 2 electrons, each one gets 1 electron. So what we're going to do for formal charges, we're going to say, well, how many valence electrons did hydrogen bring to that business? How many valence electrons does hydrogen have? 1. And if we cut it up this way, how many is hydrogen leaving with? 1. So hydrogen's breaking even. 1 minus 1 is 0. And so we would say he has a 0 formal charge. Hydrogen always ends up with a 0 formal charge. Let's think about carbon. How many valence electrons did carbon bring? 4. And how many would it leave with? 1, 2, 3, 4. 4 minus 4? 0. How many valence electrons did nitrogen bring? 5, because it's in group 5A. And how many does it leave with? 1, 2, 3, 4, 5. Also 0. So all of those are 0 formal charges, which tells me right away that's probably the correct structure. Let's look at this one over here. Again, they made this business, and then they're going to break it up. Just going to cut things down the middle. And so again, hydrogen brought one and leaves with one. Hydrogen's formal charge is always 0. Let's look at this nitrogen. Nitrogen brings 5 electrons to the business, 5 valence electrons, and how many is it leaving with here? 1, 2, 3, 4. It's leaving with 4. So that's +1. So this has a +1 formal charge. It's short an electron. It got a bad deal. And over here for the carbon, carbon brought 4 electrons, and how many is it leaving with? 1, 2, 3, 4, 5. -1. So all of these formal charges add up to the overall charge on the thing, and these all add up to the overall charge on the thing. But this shows us that this carbon would have more electron density in this molecule, and nitrogen would have less, whereas here things are shared more equally. They're spread out better. And so because all the formal charges here are 0, these are lower than those numbers, this is the better structure.
So would that second one be
Well, actually, they're both going to be polar. But this one is not going to be as stable as that one. And what we'll encounter is they're going to want you to draw the best Lewis structure, and this is not the best Lewis structure. It also, there was that guideline of the more electronegative tends to be terminal. Nitrogen's more electronegative than carbon, and here it's not terminal. And so that's another clue that this is not as good. Any questions? So for formal charges, this goes back to what I said about looking at the atoms. So carbon, right, has 4 electrons, and nitrogen has 5, just as an atom. And then if we're looking at how many of those are unpaired, carbon has 4, nitrogen has 3. If nitrogen makes 3 bonds and has an octet, it will have a 0 formal charge. So here, nitrogen has its octet and 1, 2, 3 bonds, 0 formal charge. If carbon has an octet with 4 bonds, 1, 2, 3, 4, it will have a 0 formal charge. So that can help you. Carbon's usually going to have 4 bonds. Nitrogen's usually going to have 3 bonds. Oxygen's usually going to have 2 bonds. Halogens are going to have 1 bond most of the time. Assign formal charges to each atom in the 3 resonance forms of N2O. N is central, which we might not expect, but that's why they told us. Which resonance structure is likely to contribute most to the correct structure of N2O? So we're looking for the one that has the lowest formal charges, all 0 if possible. Well, if we look at this one, and again, thinking about nitrogen and oxygen and nitrogen and the number of valence electrons, bless you, and the number of unpaired electrons that we get. Nitrogen is going to need to have 3 bonds to have 0 formal charge, and oxygen needs 2. And so we can look at this and see, well, here, oxygen has 2 bonds and an octet. So that oxygen probably has 0 formal charge. Let's check. I'm going to find the formal charges. We're just going to cut the bonds in half. Think about how many did it bring to the business and how many is it leaving with. So oxygen always brings 6 electrons when it gets involved in business. You can quote me on that. And how many would it leave with here? It gets half of the bonding electrons, 1, 2, 3, 4, 5, 6. 0. So this oxygen has a 0 formal charge. Do you think these nitrogens have 0 formal charges? Does either of them have 3 bonds? No. So they're both going to be non-zero. Let's figure out what they are. So the first nitrogen brings 5 electrons, and how many does it leave with? Leaves with 6. So that's a -1 formal charge. And the guy in the middle brings 5 and leaves with 4. So that was +1. Okay. Let's see if we can do better over here. Do any of these nitrogens have 3 bonds?
Yes.
Yeah, this guy on the end, right? So I'm going to predict that his formal charge is 0. Let's check. Brings 5, leaves with 5, 0. This nitrogen has 4 bonds, so that's not going to work out as well. Brings 5, is going to leave with 4 electrons, so +1. And this oxygen would like to have 2 bonds, and it doesn't, so this is also going to have a formal charge. It brings 6, it leaves with 7, -1. That doesn't look like a positive one, it looks like a weird H. Do any of these have 0 formal charge? No. This nitrogen has 1 bond, it wants 3. This one has 4, it wants 3. Oxygen has 3, it wants 2. So there's going to be formal charges all over the place here. The guy on the end brought 5, and how many is he leaving with? 7. So that was -2. Oh, this is not good. And the guy in the middle brought 5, leaving with 4. He's in the same situation as this guy. So +1 formal charge. And the oxygen on the end brought 6 and leaves with 5, -1. The one that's going to contribute most to the resonance structure is the one with the lowest formal charges. And, you know, if you're a math person, you could say, well, you could look at the absolute value and sum up. So make them all positive. We've got 2 + 1 + 1. This is 4. And that would be 2 and 2. So these are better than that.
So we're going with the lowest absolute value?
Yeah, lowest absolute value. So that's not the best one. Now here, we have +1 and -1 for both of these, but we need to think about, well, where is the negative charge and who's more electronegative? Oxygen's more electronegative, and here the negative charge is on the oxygen. That means the extra electron is over here, which would make it happy because oxygen is more fun to play. The oxygen house is more fun to play at, and so the electrons prefer to be there. So this is the one that's going to contribute the most. Good question? Yes, it is. It is, thank you. This is +1. Lost my ability to do simple math. Yeah. Because these charges all have to add up for these to 0, and it didn't. Thank you. Any other questions? So again, this reminds me of my husband and me and our children. All my ancestors came from Sweden. All my husband's ancestors came from Japan. So our little resonance hybrids, some of them aren't so little anymore, we did not contribute equally to their appearance, as you can imagine. All the children look much more like my husband than they do like me. And if you look carefully, I am in there. Right? So. Okay, drawing resonance structures and assigning formal charges for organic compounds. Draw the Lewis structure, including resonance structures for diazomethane, CH2N2, C is central. For each resonance structure, assign formal charges to all atoms that have formal charges. Okay, so they told us the carbon's in the middle. So you might say, well, let's do nitrogen. Let's just stick everything on the carbon. There it is in the middle. That looks okay. Carbon has 4 valence electrons, 2 hydrogens each have 1, and 2 nitrogens each have 5. So that's 10, 12, 16. Did I do that right? So 2, 4, 6, 8, 10, oops, 12, 14, 16, ran out of electrons. The way I drew that skeleton, this is a puzzle that cannot be solved. In order to get an octet for nitrogen, I would have to take a lone pair from carbon and share it to make a double bond, but carbon has no lone pairs. So this tells me that I drew my structure wrong. I did that on purpose. I actually did. So, well, oh no, I don't want to do that. Let's just start over. Take off the whole thing. So carbon in the middle and nitrogen. Well, if we don't put the hydrogens on the carbon, we could put them on the nitrogens. So let's try putting one on each side. Still 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. So this nitrogen has an octet, but the carbon and the other nitrogen do not. So I need to take a lone pair from the nitrogen and share it with the carbon to make a double bond. So nitrogen 2, 4, 6, 8, carbon 2, 4, 6, 8. This nitrogen, not happy. So I'm going to take from this neighboring atom that has enough and ask them to share this lone pair so that everybody can be happy. I suppose you could call that redistribution of wealth. We don't want to get into that. There. Everybody's happy. Well, we have 2 double bonds. There are other ways we could arrange those double bonds, the extra bonds. So here's our skeleton again. What if we made a triple bond and a single bond instead of 2 double bonds? It's the same number of electrons. So we've got 2, 4, 6, 8, 10, 12, 14, 16. I'm just rearranging the electrons and do it that way. Perfectly good Lewis structure. But why does this nitrogen have the triple bond and that one doesn't? Well, there's no good reason. So let's, settle this argument here and do it the other way also. And so these are 3 resonance structures. The actual structure is kind of an average of those. And then it says assign formal charges. So assigning formal charges, if you do the electron subtracting thing for every atom, gets a bit tedious. Hydrogen's always 0, just leave him out of it entirely. And if we're thinking about the nitrogen and the carbon, so again, just thinking about the valence electrons that they had as individual atoms, right? Carbon, we predict, would have 4 bonds to be 0 formal charge, and nitrogen would have 3. So over here, this nitrogen has 3 bonds, this carbon has 4 bonds, this nitrogen has 3 bonds. I think everybody's good over there. Let's check. Now cut the bonds up. Nitrogen brought 5, it leaves with 1, 2, 3, 4, 5. Carbon brought 4, leaves with 4. Nitrogen brought 5, leaves with 5. All 0 formal charges. That's good. Let's look over here. Does this nitrogen have a formal charge? Yeah, because it's only got 2 bonds, right? So it's not 0. So let's look at that. Brings 5, leaves with 2, 4, 5, 6. So -1. How about this carbon? Carbon likes to have 4 bonds. The carbon has 4 bonds. That one's 0. This nitrogen wants 3 bonds. This one has 4, so this is not going to be 0 either. So that nitrogen brought 5 and is leaving with 4. So that's going to be +1. And then for this guy, we can just look at what we did over here. This nitrogen is in the same situation that that nitrogen is in terms of electrons. So this is going to have a -1 formal charge. The nitrogen over here with the triple and the single bond, just like that guy, going to have a +1. Any questions?